Afterwards, I want time and all. Next week, only you will get back. After completing your holidays, instead of that, and
Dear students, am I audible? Anyone not to please respond?
Yes, sir.
Okay. So within few minutes, our guest lecturer will join. Just wait for a few minutes. Good morning to all the students. This is head of the department, Dr. Logesh. Madam has joined. Till now, third unit I've covered in today's session. In the last session, Madam started fourth unit introduction. Today, fourth unit sessions are going to be continued. Please kindly mute your audio and video unless if asked any questions. If you have any queries or any doubts, you can switch on your audio, then you can raise your doubt. Unless do not use your video and audio until completion of the session. Thank you. Madam, Dhanlakshmi madam. Hello, madam. Madam, your voice is not audible. Dhanlakshmi madam.
Now it is audible.
Now it's audible, ma'am.
Thank you, thank you, thank you. Yes, sir, yes, sir. Fine. 1 second, sir. I will share my screen. Audible, fine. Thank you. Okay. Okay. So today we are focusing on quantum communication and computing, theoretical perspective, that is unit 4. Last class we started with this. Students, it is audible, right? It's audible, right? Hello?
Yes, ma'am.
Okay, fine. So last class we were discussing about this difference between quantum and classical information. Okay. We'll see the overview on this. So how our quantum communication is going to differ from classical information communication. And you know very well, in quantum communication, we are transmitting the information using the principle of quantum mechanics, and we are using the concept like superpositioning and entanglement. That is going to create you highly secure, unhackable communication channel. Apart from that, we are also going to include the secure data transmission and quantum key distribution, which is going to help the quantum phenomena to detect the any attempt of hacking. Okay, so that is why this technology offers revolutionary security for industries like banking, defense, healthcare. That is the main reason. So the main reason is your quantum communication is going to provide more security than classical information. Why? Can anyone tell? Why quantum communication? Please mute everyone. Why quantum communication going to provide you more security than classical communication? Can anyone tell? You know about this no cloning theorem? In quantum communication, we take the support of no cloning theorem. Whenever we try to do any copy of the quantum information, immediately we can make it will not allow actually in quantum communication, it will not allow for duplication. That is one reason. Okay, another reason, if anyone hackers trying to try to access our information, your quantum state will collapse, it will change, so that we come to know that some hacker is trying to trying to take our data. So because of the basic principle on which the quantum technology is working, it helps us to detect the hacker. Immediately they try to access our information. The quantum states will change. With this disturbance, we can make out that some hacker is trying to detect the data. Okay. So that is the main reason behind this quantum communication. We are going to provide, it provides you more security. It is going to provide you unbreakable security. Okay. So, and then you know that in quantum communication, we are going to use quantum bits, and it is going to work on the laws of quantum mechanics. And this is the main thing you have to remember when you're talking about quantum communication. The properties of the quantum mechanics is no cloning theorem. Okay, which make it impossible to copy the quantum state without detection. Okay, offering potentially unbreakable security. This is the main thing. This is one point that quantum communication supporting no cloning theorem, which make it impossible to copy the quantum state without detection. Okay, we can detect when somebody is trying to copy, we can detect it. Okay, and it is going to provide you unbreakable security. Apart from that, with these concepts like superpositioning and measurement effect, entanglement, these are all helping us providing these features gives more security. Okay. Coming here, when I focus on my classical communication, I know very well that here we are trying to use as we know that we are working with the bits, and your classical systems are there, no, are deterministics, whereas your quantum systems are indeterministics, and their state collapses upon observation, providing built-in hacker detection for quantum communication. So this is what you should try to remember. The main difference between your classical communication and quantum communication is classical communication are deterministic, whereas quantum communication is indeterministics. So what is happening in quantum communication? As soon as the hacker try to hack the data, immediately you can observe some changes happening in the quantum state. And the states start collapsing. So immediately we'll come to know some hacker is trying to detect trying to attack our data, and we can detect that. Okay. So, but in classical communication, it is deterministic. Even though hackers coming and accessing our data, we can't detect immediately. We'll not come to know they are trying to trying to access our data. Even though hackers is accessing our data, we can't detect that. It is immediately we can't detect that. Later we may come to know, but immediately we can't detect that because it is deterministic. It is fixed. We can't make out. And another reason is in classical communication, it is going to rely on complex mathematical algorithms, okay, for encryption. So which may be easy for the changes to the future computational power. So coming here, since in classical communication, information transfer is deterministic, meaning the exact path and the states are known. Okay. Whereas in your quantum communication, it is indeterministic. Okay. Fine. Now you will compare these two things. One is quantum communication with our classical computing. So we are going to compare this quantum communication with classical communication based on three things. One is how the information is represented in both in quantum communication and also in classical communication, and how the data is transmitted in case of quantum communication and in case of classical communication, and how data is processed in quantum communication and in classical communication. The first one is how the information is represented in both classical and quantum. So if you focus on in classical, we are using zeros and ones, bits only we are using. In quantum communication, we are using qubits. So we can represent here 0, 1, both 0 and 1 simultaneously because of the concept of superpositioning that you are know. And then here, when you're using this encoding concept, here in classical communication, we are focusing on voltage level, pulses, binary signals. Whereas in quantum communication, we are focusing on quantum states of particles. That is a polarization of photons. There is a horizontal polarization, vertical polarization. Okay. Now coming here, the medium for transfer in classical communication is wires, optical fibers, and wireless is available. Whereas in quantum communication, we have quantum channels. Okay, fiber optics for photons. And the signals are here electrical and optical pulses. Here we have quantum states like spin and polarization. It depends on the qubits. If you are using spin qubits, they are using the spin they are using the spin energy. If you are using photons, photon qubits, then they are going to use this polarization. Okay. One second. Fine. Now coming to next is how in classical communication, it is easy to duplicate. We can copy. Whereas because it is supporting this no cloning theorem, you can't copy. Okay, you can't clone the qubits. So this is one thing because of this, the security is high here, I can say. Then coming here, in your classical communication, for example, where the encryption techniques are used. Some algorithms are there, like RSA is there. One example. Whereas in quantum communication, intrinsically secure via your quantum key distribution. Okay. And here in classical communication, if any a hacker is trying to access your data, it is very difficult to detect. Okay. But here you can detect the hacker very easily in quantum communication, because your quantum signals will get disturbed. Immediately we can notice that, because of this, the principle of quantum communication is like that. The quantum states, immediately somebody is trying to access the quantum information, the states start changing. So immediately we'll come to know some hacker is trying to attack our data. We can detect that very easily. Now coming here, the key concepts in both the communication is like in quantum communication, we are using this superpositioning and entanglement, and one more thing, quantum teleportation. Okay, the way you try to transfer the quantum information using entanglement and classical communication. Now coming in classical communication, we are trying to, if we focus on internet and networking, we are using standard data transfer. Whereas in quantum communication, we are using quantum internet secure key exchange. Okay. And if you focus on the area cryptography, in classical communication, it is very easy to attack. Okay. Easily hackers can attack. Whereas quantum communication provide you safe, unbreakable encryption. What is the reason? Can you tell? Why quantum communication is more safer than classical communication, and it provides you, it enables unbreakable encryption? Students, why quantum communication provides you quantum safe, enables unbreakable encryption? How? How? Because in quantum communication, it supports no cloning theorem. Whereas in classical, you can easily copy. You can clone the bits. Here you can't clone the bits. No cloning. Okay. And another thing is that if a hacker is trying to attack the basic quantum mechanics, the basic principle in quantum communication is that as soon as somebody try to access our data, immediately the quantum signals start changing. It get disturbed. So immediately we'll come to know. Whereas in this classical, we can't make out that changes. So very difficult to detect the hacker in case of classical communication. So once it is, I'm able to detect the hacker immediately. A hacker is trying to access. I can enable my security, right? So it is quantum communication is more safer. Okay. Long distance secure communication, yes, it is easily they can tap, but here we can make unconditionally secure via quantum key distribution. Okay, so the two things we are now we are going to focus on this. If it is a very long distance communication, you can take the support of this quantum key distribution, and you can provide secure communication, and you can provide secure communication. Now, finally, the main difference summary, if you see, in classical communication, I'm using bit. In quantum communication, I'm using qubit. And can I copy the data in classical communication? In classical communication, yes, sure, I can copy the data. Whereas in quantum communication, you can't do the duplication. No, not possible, because of no cloning theorem. And in classical communication, it is based on mathematics. Whereas this quantum communication, it is based on quantum physics. So since it is based on quantum physics, the nature of your quantum physics, as soon as somebody is trying to access the data, your quantum signals start changing. So easily we can detect the hackers. Some hackers are trying to access the data. Then immediately you can use appropriate QKD, that is quantum key distribution concepts, and you can enable the more security you can enable. Okay. here the hackers is hard to detect in classical communication, whereas in quantum communication, it is easy to detect because as soon as somebody is trying to hack your data, the signals in quantum signals start changing. It get disturbed. It will collapse. That is the nature of your behind your quantum computing. Now coming here, this is limited by classical limits, okay, speed and all. Whereas here it is exponentially, you can speed up quantum technology. You know very well why we are going to quantum computing, to fastness. We need to have supercomputation, right? For that reason only. Now coming here, the next is that. Okay. Now tell me, which is more safer, whether classical communication is safer or quantum communication provides you more safer? Student? Hello? Hello? Quantum communication provides you more security or classical communication provides more security? Where in which communication we can detect the hacker and in which communication it is difficult to detect the hacker? In quantum communication, whether it is difficult to detect the hackers? Hello? In quantum communication, it is difficult to detect the hackers?
Yes, ma'am.
No. It is very easy
Quantum
to.
communication లోనే కాదు.
In quantum communication, we can easily detect the hackers because as soon as they try to access your data, if somebody is trying to access your data, the quantum signal changes, it disturbs. Okay, the basic characteristics behind your quantum communication, quantum principle is like that. Your quantum signal start changing. Somebody trying to access your data, it comes to know, it will start changing because, and also it is supporting no cloning. Nobody can do duplication. Your qubits, immediately some change will happen in the output. Then we come to know that somebody is trying to hack our data. Immediately we can provide more security. So it is very easy to find the hackers in quantum communication. Then according to that, we can provide more security by creating appropriate quantum key distribution techniques. Yes? Hello? Hello? But in classical communication,
Yes,
it is
ma'am.
still but in classical communication, since it is deterministic, it is very difficult to find the hackers. Okay. Okay. Now coming here, the quantum communication. Why? What is the technology behind this quantum communication? How we can easily find the hackers? As soon as they try to access our data, we can find them very easily. We can find what is the concept behind this, because quantum communication encodes the information in quantum states of particles like photons. Okay. To achieve secure communication and advanced computing, by exploiting this quantum mechanics principles such as superposition, entanglement, and measurement effect. These concepts are there, no? Superpositioning, entanglement, measurement effect. It helps, it will going to give you more secure communication. This superpositioning, entanglement, and measurement effect, it is going to help you to achieve more secure communication. This principle is allowing you to detect the hackers. Okay. How? Because as soon as your quantum states get changes, right? Once they start accessing your data, there will be some disturbance in your quantum states upon measurement. Okay, then I'll come to know, yes, then I'll come to know the hackers have, I can detect the hackers. Fine. So enabling the creation of secure cryptographic key. So once you come to know that, yes, somebody is trying to access your data, you can enable cryptographic keys like quantum, it is supported by quantum key distribution. Your quantum key distribution helps you to provide you secure cryptographic keys. Okay, that will try to help you to connect all the quantum computers in the network so that you can have a secure communication. But some challenges are there here in quantum communication. There is a signal loss over a long distance, okay, which may cause the error. Okay, so we require some robust channel like optical fiber and leading edge technology to reach, to increase the reach and data rates. So in case if you have a long distance communication, if you're trying to do, you can also have some quantum repeaters. If there is a signal loss, no, you can have quantum repeaters in center between the long distance. Yes. Hello. Any doubts? Any doubts, students?
No doubts.
Okay, shall I continue? So, the basic thing what you should remember here in quantum communication, it provides you more, it is more safer. Why it is more safer? Because it is supporting no cloning. It will not allow duplication of the qubits. Okay. Another thing is that as soon as your hacker trying to access your data, immediately quantum signals start changing. Okay, then I can detect the hacker very easily. But in classical communication, to detect the hacker is very difficult. It is something deterministic. Okay, it is something fixed. It is very difficult to detect the hacker. And apart from that, once I come to know somebody is trying to detect my data, I can enable the secure cryptographic keys like quantum key distribution concepts. I can enable that, and I can provide a secure communication over long distance. Then also some signal loss will be there. For that, you should use quantum repeaters in between. Fine. So this is the main points you should remember on quantum communication. Quantum communication is more safer. We can detect the hacker very easily. Okay, and also because of these features like superpositioning, entanglement, measurement effect, because of these only I'm able to identify the hackers. These are not supporting me to detect the hackers easily. Okay, now coming here, now how this quantum communication is going to work. First of all, whenever you are sending the data from one point to another point, we have to encode them. Okay, the information to be encoded. Whatever you have to encode the information into the quantum states of particles. Okay, yes, if you are using photonic qubits, your particles will be photons. Fine. If you are using the spin qubits, your particles will be some spin energy. Okay. So if you have to, whatever the information you are trying to transfer from one end to another end, you need to encode that into quantum states of particles. If it is photonic qubits, you have to use the particles will be photons. Okay. If you are using spin qubits, your photon states of particles will be spin. So most commonly, we'll be using this photons. If I focus on photonic qubits, I'll be using this. The quantum states of particles will be photons. So your information will be encoded in these photons. Okay, fine. Now coming here, what is the encoding method you are trying to follow there? So your photons can encode the information in various ways. How the information, your qubits data is encoded in the photons? They are using the concept here. The concept is known as polarization. Okay, by using this polarization concept, there are two types of polarization. One is horizontal polarization, another one is vertical polarization. By using this, I can encode the information, okay, into the photons. Okay. Okay. So next is how once after encoding the information into the photons by using the technology polarization, now we need to transfer this data securely. Now these quantum states, whatever your quantum states or quantum information that is encoded in the form of photons by using the concept of polarization, we need to transfer this over the quantum channel. The base for the your quantum channel can be optical fiber. You can use optical fiber as your quantum channel for transferring your quantum information. Okay. Now when you focus on your detection and verification, when the receiver measures the incoming quantum states, any disturbance is there. Okay. Suppose if hacker is trying to attack the data, immediately the state will start changing. Your quantum states, no, it will start changing, so that we can detect the yes, definitely it is not, the security is not enough. People are trying to hack our data. Then you have to enable the QKD, that is quantum key distribution. Okay. So here how here the overview is, you should remember that our information is encoded into a photon. If you are using photonic qubits, then how our information is encoded into photons? By using the concept of polarization, either horizontal or vertical. Once the your information, or I can say quantum states, okay, is encoded in the photons. Now I need to transfer this across the quantum channel. I may use optical fiber. While transferring my data across the quantum channel, if hacker is trying to hack my data, immediately my quantum states or my information will start, whatever the quantum states, no, that will start changing. Okay, then I come to know that yes, hackers are trying to attack my data. Then you have to enable more security, high security you can give by using this concept of QKD. Okay, now to provide secure communication, you are going to use this quantum key distribution. So when you are transferring your data across your quantum channel, after encoding your information, when you are transferring your data across your quantum channel, you have to provide security. You're using this concept known as quantum key distribution. Okay. See, this quantum key distribution uses the quantum properties to generate the distributed secret keys for encryption. So your QKD, that is quantum key distribution, going to use this quantum properties to generate the secret keys for encryption. Okay. And so that if your hacker is trying to hack, if he is trying to hack, immediately I can detect. Okay. Immediately if a hacker is trying to hack my data, I can detect that. I'll come to know that in case of my quantum communication. Okay, quantum networking, focus on this quantum networking. So many computers will be connected across your quantum network. And our goal is that whenever you are transferring the data from one quantum computer to another quantum computer across the network, security is very, very, very important. By using this concept of quantum key distribution, I can provide by generating secret keys for encryption and decryption. I can provide the secure communication among the quantum computers in the network. Okay. So quantum computing enables communication between distant qubits or quantum computer for distributed quantum processing. Okay. Now, what are the challenges? What are the problems I'm facing to provide a secure quantum communication? Why I'm not able to provide secure quantum communication? One is that one challenge is loss. Okay. Your quantum states are encoded in photons, they get lost or scattered in the optical fiber. Okay. So there will be some error leading to that, some error will be there. And if the distance is more, definitely your signal loss will be there, signal degradation will be there. Okay, that is the another limitation. Okay, challenges in quantum communication. Another one is decoherence. This is due to the quantum states are fragile. It get easily disrupted by the environmental noise. Okay, a phenomena called as decoherence. That is what I said. No, your quantum bits it start changing as soon as it try to interact with the environment. Okay, once it is getting affected by these magnetic rays or cosmic rays, your quantum states start changing. Okay, then naturally the state, the output starts collapsing. Okay, so that is known as decoherence. But we need our goal is that we should have a long coherence. Okay, but the basic technology behind your quantum principle is that it is like that. Once it start your qubits interacting with the environment, it goes to decoherent states. So these are the challenges are there. Photon loss. Okay, then distance, long distance. Then this decoherence. How's it? Okay, these are the challenges. Okay. Now, yes, ultimately the summary is quantum communication opens door to unbreakable encryption, and it provides you quantum internet and next generation, we can provide next generation secure messaging. Okay, these are the things are possible. Okay, so in the quantum communication, you should focus like this. The thing is that one is that what I can say, it is quantum communication is more safer. Okay, quantum communication is more safer, and it enables unbreakable encryption because of the technology behind the quantum communication supports is no cloning theorem is there, and you know very well where your quantum signals, so if hackers trying to access the data, quantum signals start changing. Okay, because of these principles, technology behind your quantum technology, we can identify, you can detect the hacker very easily. So once you come to know that, you can provide more security, high security, by using the concept of QKD, that is quantum key distribution, which is helping you to generate the secret keys for encryption and decryption. Okay. Now, next we are focusing on quantum key distribution. Okay. Quantum key distribution, it is one of the most important practical application for quantum communication. This is going to generate the shared secret key. Okay. Which is going to provide you more secure, even when the hackers with the quantum computers. So even though a hacker is trying to access your data across your quantum network, if you try to use this quantum key distribution concept, you can secure your data. So actually this quantum key distribution, it is helping me to generate the sharing secret encryption key. Okay. Okay. Using the principles of quantum mechanics. Okay. So it will ensure you communication is secure even against the your future super fast quantum computers. So here also we will be having two parties as we studied in the classical communication, Alice and Bob. That same example you can take. One person one side they are sending the data, another person is trying to receive the data. Alice is trying to send the data. Bob is trying to receive the your quantum data. So what will happen now? If any hacker is trying to access these qubits, okay, your quantum state starts changing. Immediately start changing, and immediately you can detect that hackers are trying to access your data. Whereas in your classical communication, no, even though hackers trying to access your data, it is difficult to identify the hackers. It is difficult. Okay. Here it is easy to identify. Now your QKD is a cryptographic method that uses the quantum mechanics to securely distribute the encryption key. Okay, the security is based on the quantum principle, whereas in classical communication, the security is based on mathematical complexity. Okay, we will be using complex mathematical concept for providing the security. Here you are using quantum principle. And the quantum principle itself, what are the quantum principles? Your superpositioning, entanglement, measurement effect, and as soon as anyone start accessing your data, your hackers, the quantum signals start disturbs. It will get disturbed. Okay, and it starts collapsing. Because of these features, I can identify the hacker immediately. Okay. Now, how this is going to work, your QKD? your quantum key distribution. The first they are focusing on quantum key generation. Okay. The communicating party generates some secret random keys by manipulating and measuring the quantum particles such as photon. Next, in your QKD, we are using quantum channel. You may use the optical fiber as a quantum channel for transferring your data. And in your to detect the hackers, we have some fundamental laws of quantum mechanics, such as no cloning theorem, okay, which will not allow the duplication. And we have another concept, a measurement disturbance, okay, measurement disturbance principle, which will, it will help you to find the hacker, we can detect the hacker easily. Okay, then error detection. As soon as hacker is trying to access your data qubits, you can immediately, there will be change in the quantum signals. Immediately you can find some changes are there, some transmissions errors changes will be there, errors will be there. So immediately you will come to know, you can detect the hacker. So these are the main concept how your QKD is going to work. And the principles behind your quantum communication, we are using superpositioning, entanglement, and you're using this no cloning theorem, and you're using this measurement disturbance principle, and unconditional security. Unconditional security. Hello? 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 Students, it's audible? It's audible? It's audible?
Yes, ma'am.
Okay, fine. We'll continue after 10 minutes. 10 minutes break you take. Here also some disturbances there outside. After 10 minutes, we'll continue. You can take 10 minutes break
Okay.
and again you can join. Okay?
Okay, ma'am.
Okay.
Yeah.